Hello YouTube, it's Troy again from The Lonely Wolf and welcome back to my channel. So today I'm going to continue on with a series of videos. So I've been dealing a lot with the philosophy of mathematics. So they're videos I've done quite a while ago, so I'm going to continue with that. Okay, so the topic of today's discussion is 2 plus 2 is equal to 4. Okay, so we're going to look at the truth of that statement. Okay, so let's have a look at some of the connotations the minute that I bring this up, because I know that it's something that people have argued about a lot. Okay, so number one, okay, the first connotation we have is George Orwell's 1984, that the freedom means the ability to say 2 plus 2 is equal to 4 rather than 5. Okay, or some people might associate any sort of skepticism with postmodernism, that we're trying to destroy mathematics, that we're trying to encourage people to say, well, 2 plus 2 can be whatever number we want and we'll throw away all of previous mathematical knowledge. Okay, so while I reject, that sort of claim, so I come from none of those places. Okay, so I'm not using any sort of postmodernism, any critical theory whatsoever. Okay, I am going to make the case though that mathematics is more complicated than what we think. So let's begin. Okay, so we're going to dive into this. Okay, so somebody's written on the board 2 plus 2 is equal to a 4. So first of all, I want you to ask yourselves, what assumption did you make when you looked at that equation and you've agreed with that? So pause the video for a moment and have a think about what assumptions you made. The next part I want you to think about is what part of this is socially constructed. So what does social constructivism have to do with mathematics? So take a moment if you want to press the pause button and have a think about those questions. Okay, so the pause should be over. Okay, so I'm going to go through some of the assumptions that we make when we do this. Okay, so number one, okay, we're dealing with integer values. So when I talk about integers, I mean the whole numbers. That includes 0, 1, 2, 3, 4, and we can include negative numbers. Okay, so as long as they're whole negative numbers, then we're good. So we're dealing with integer values. So that statement is true. We have to make the assumption of that. Now, this is an argument that I've seen. Okay, so if we put 2.3 plus 2.6 equals to 4.9. So it's accurate if we have 4.9, but if we wanted to round that up, we could round that up to 5. Okay, so some people have made the argument that, okay, that says that 2 plus 2 could equal to 5. So let's write that down. Okay, that's really not the best reasoning. I really disagree with this reasoning and I don't go for this. Okay, the reason why is because, this is a very gross simplification. So the equal sign is very, very important. We want the left-hand side to be equal to the right-hand side. Okay, that's what we do in mathematics. Okay, now if we were rounding up to 5, we'd lose a lot of information. So, we want the left-hand side to be rounded and we want the right hand side to be rounded to show the inequality. Okay, so I'm going to put a cross against that to say that that's a case, but that's an interesting thought experiment to make though. Okay, the other assumption we're making is the purpose is we're counting objects and we're assuming that each of those things are identical. Okay, so we have 4 objects and we're going to assume that those things are identical. So that's something we think about as well. Now, the big assumption, this is a huge one. The real world problem is going to call for this equation. Okay, that's going to be something that I really revisit. I'm looking at the relationship between the real world, which has people and people making contributions to mathematics, and the mathematical world of abstraction. Now, what I'm going to do is look at some interesting cases that might sort of open your mind up. Okay, so I'm not challenging any fundamental mathematical ideas. Okay, so number one, counting in different units, carrying stick problems, modular arithmetic systems, and the time value of money. So these are sort of interesting cases that show the relationship between, I guess, the social use of number, or I guess the social construction of things, as well as the abstract mathematical world. Okay, this is a very important framework I want you to understand. So what it means to work mathematically. So this is really how we go about problem solving. Okay, so we have the real world and we have the abstract world or the purely mathematical world. So what we have is a real world problem and we have a situation. Okay, so what we do is we want to simplify that problem and we want to convert that into, I guess, some sort of mathematical model. Okay, so that could be a graph, it could be an equation. Okay, so 2 plus 2 equals 4 is an example of a mathematical model because it's an equation that's used to represent reality, okay, or an approximation to reality. And then we find the solution within the model. So within the mathematical world, 2 plus 2 equals 4. Yes, absolutely true. But what we're going to be really looking at is how that translates to the real world. Okay, so did that equation hold true, or is it the best equation in terms of the real world problem we're looking at? Okay, so the first thing I'm going to look at is called the counting problem. Let's say that I give you 2 boxes. I give you another 2 boxes. Okay, altogether I have 4 boxes. Okay, so we'll write our equation. So this is the real world problem. We're counting the number of boxes. Okay, the mathematical model we're going to make is 2 plus 2 is equal to 4. Okay, so when I ask you what was socially constructed about this, okay, the thing that's mainly socially constructed is the fact that we're using a convention. We're using an equal sign, we're using a plus. So we're using language to communicate things that we know about the real world and translating that into something that we all understand. And we're using a convention that we all agree on. So it's very much a social transaction we're doing. Okay, so far so good. So let's add a little wrinkle. Let's say that the boxes contain apples. And we think, whoops, okay, what's gone wrong here? Okay, so if we count apples, we now have 5 apples. Okay, so our equation has actually been changed. So what's happened now is we've made a mistake. So we've thought, okay, in the real world, we were looking at boxes, but then in the real world, we're also looking at apples as well. Okay, so what we have to do is go back into the real world and reformulate our problem. So we're not counting the number of boxes anymore. We're counting the number of apples. So if we go from the real world into the abstract mathematical world, we have to change our equation. Okay, so the equation is going to be reformulated as follows. So it's going to be 2 plus 3 equals to 5. Okay, so what happened here? Okay, so in the real world, okay, we started off by formulating boxes, and we wanted to count them. And then in the abstract world, we said that 2 plus 2 is equal to 4, because an equation is basically a mathematical model of reality. But then when I asked you to count apples, we have a different equation now. So it's going to be 2 plus 3 equals to 5. Okay, so the big mistake that some people might make is that I'm not going to be dishonest with you, and I'm not going to say that 2 plus 2 could equal to 5. Okay, because that wouldn't make sense. I think the reality is that what happened is that we had to reformulate our problem and we had to use the correct equation, not this way around. Okay, the other problem is it's called how many sticks. It's just something I invented. So imagine that your task is to carry 4 large sticks and you want to build a shelter. Okay, so we could use the equation 2 plus 2 is equal to 4. There's 2 sticks here, there's 2 sticks there. There are 4 sticks altogether. But it really depends on what our purpose is and what the activity is. So let's have another look at another theoretical approach. Okay, so when we talk about doing mathematics, okay, so there's really mainly 5 activities we're doing when we're doing mathematics. Okay, so something that's concrete and something that's material. So this is a physical thing, so it's an action and a model. So if I talk about carrying sticks, I'm really talking about a physical activity. It requires you to exert physical activity. But there's also representations. Okay, so we could use graphs or number lines. It's also the context. So we're applying the maths to the situation. Now, verbal, that's something that we do between each other. So if I explain to you the reasoning, that's a verbal communication. And most importantly, our symbolic. So it's our expressions, it's our equations. So 2 plus 2 is equal to 4 is an example of a symbolic representation. But what we're going to find with this problem here, so that's an example of a symbolic representation. But does that really match with the physical model we're doing? Okay, because the physical activity we're doing is we're carrying 4 sticks. Now, since our activity is carrying those sticks, do we really care how many that we have? Okay, are we trying to count them or are we trying to carry them? So what if the sticks had different weights? Okay, so we could have 3 of them that were roughly the same size, but another one was a lot of size. So if you measured them in kilograms, for example, and they all add up to 5 kilograms, okay, so this, even though in the mathematical world, 2 plus 2 is equal to 4, okay, yes, that's correct. But in our physical world, it doesn't even matter. It's got no bearing because, when it comes to strength and physical activity, okay, if one of those sticks are heavier than the others, then it doesn't feel like we're lifting 4 sticks. it might feel like it's kind of irrelevant if one stick is going to be heavier than the other if we're trying to build shelter. Okay, so sometimes when we sometimes challenge these ideas, we're looking at the dissonance that lies between the physical and the symbolic. Okay, that's really what complicates mathematics a lot more, and that's what really makes it a human endeavor rather than simply a purely abstract or purely objective type of activity. Okay, let's have a case. Okay, what if I was to tell you that 7 plus 7 was equivalent to 2? Under what circumstances? Okay, so I'm going to show you how that can come to be. So let's use the clock system. So let's say that it was 7 p.m. and I wanted to add 7 hours to that. So this is actually called modulo 12 arithmetic. Okay, so what we have is we have 7 p.m. and if I plus 7 hours. Okay, so that's going to give you 14. So let's say it's 14 o'clock, but there's no such thing as 14 o'clock because you know that 14 o'clock is equal to 2 o'clock. Okay, so what it says is 14 is equivalent to 2, and that's called modulo 12. Okay, so we call it modulo 12 is because once we reach 12, that's called our reset. So it's almost like we do a reset and we reset it back to 0. Okay, so this is something that you've done before. Even the most basic knowledge of mathematics, we can do this. Okay, this is something we do every day. Okay, we do time calculations. Okay, but what you're not aware of what you're doing is you're actually doing modulo arithmetic as you're doing that. Okay, so in this case, we're saying that 7 plus 7 could be equivalent to 2. Okay, in the modulo 12 system. Now, we're not going to say that 14 is equal to 2. And we're not going to say that 7 plus 7 is equal to 2. Okay, that would be dishonest of me to actually do that. But what we can say is we could say they're equivalent to each other in the modulo 12. Oops, that's very messy, that writing. Okay, I'll get used to the calibration if I think about that. All right, so what if we're no longer using the modulo 12? What if we're using 3, for instance? Let's have a look at that. Okay, so what that means is we're going to have a clock, but we're going to divide it into 3. Let's say there's 3 hours in the day, to use an analogy. Okay, so we're going to divide it into 3 different sections. Okay, so the reset time is once we reach 3, we reset, go back to 0. Okay, so we go 1, 2, and then we reset back to 0. Okay, so 2 plus 3, how is that equivalent to 2? Okay, well, the equation 2 plus 3, that's equal to 5. Okay, so how do we convert 5 into our modulo? Okay, it's like this. Okay, so we go 1, 2, 3, and we reset 4 and 5. So we land back at 2. So it's almost like resetting our time. Okay, so we can say that 2 plus 3 is actually equivalent to 2 in this system here. Okay, so that's just another example of how we kind of question mathematics. So this doesn't alter the fact that 2 plus 2 is equal to 4 under the assumptions that we're dealing with integers. Okay, it doesn't invalidate that, but it kind of expands our mind and gets us to think a little bit more. Okay, here's another interesting problem. So I receive $2 now and another $2 in a year's time. So how much money altogether? So the most obvious way that you could do that, so in the real world, we're dealing with money. Okay, so in the abstract world, we could have an equation, 2 plus 2 is equal to 4. Okay, so we could say we have $4 altogether. So that's an example of a mathematical model used to represent the real situation. Now, immediately you can see there's a problem with that because the time difference, because money has time value. So we have to factor in interest. Okay, so we'd rather receive money now than we would in the future because the time value of money, because we're not factoring in interest. Okay, so if we wanted to improve that model, we could say that the total amount of money is, okay, it's $2 that we receive now. So let's draw a timeline. So we receive $2 now, and then we receive $2 in the future. Okay, so that amount of money we receive now, how much is it all worth in the future? We have to change that $2 into what it's worth in the future. Okay, and we do that by the process of doing interest. So we'd have to actually look up and think, okay, for the best model, we'd have to look up what the interest rate is if I was investing $2 for, let's say, 1 year. Okay, so let's say it's 1 year. and we think, okay, how much is $2 worth in 1 year? We have to apply some sort of interest formula. So that's the mathematics of finance. Okay, so in conclusion, I guess the way that we can look at this. Okay, so 2 plus 2 is equal to 4. The reason that people question that is I don't think that people are questioning that. And I don't think there's a postmodern agenda to try to destroy that truth. I'm thinking we're looking at the relationship between the abstract and the real world, which has humans. Okay, we have social interactions. Okay, so even the fact that we're dealing with money, which is something that was socially constructed. Now, we wouldn't have a branch of mathematical finance if we didn't have money. So in some ways, I guess the production of knowledge in mathematics is somewhat of a social activity, and even the teaching of mathematics. Okay, so even me showing you something and communicating with you, we're having a transaction, a social transaction in which we're imparting knowledge. And if you reply and you teach me something I didn't know, then that's the construction of knowledge. Okay, so there's a social element towards mathematics. Okay, now in conclusion, I'm not going to question that 2 plus 2 is equal to 4, assuming that we're counting original units. Okay, they're all the same. And assuming that our purpose is to be counting those things, and assuming those are real integer values, then I'm not going to question that because it's a foundational truth that we want both sides to be equal. So it's the scale. That's the foundational, I guess it's a foundational knowledge that we all seem to know. Okay, I think the only question there is that how does that match up with the real world? Okay, so the only skepticism that we really have that I'm showing is that equation, is that always the best representation of what happens in the real world? Okay, if we're dealing with twos. Okay, so that's really the situation we're looking at. And in some cases, that really wasn't the best equation we could have used. Okay, so in future episodes, I'll be looking at a little bit more of mathematics, just why mathematics is more complicated than what we think. So I'll look at a number of things, how things work. So I'll be looking at fractions a little bit and how to do that. And I'll also be looking at tips. So if you're teaching, I guess you're trying to homeschool children, or you might be teaching kids, basic mathematics, I'll sort of give you some advice on different ways that you can communicate points better. Okay, so I hope you enjoyed this video. Maybe you learned something. Maybe you already knew what I was talking about. So if so, leave a like, leave a comment below, and I guess I'll see you in my next video. Okay, thank you very much for watching.